Let's do Leetcode. It's been a while. I recently started a new job, but still have time now, so cool. Range sum query mutable. Given an integer array nums, handle multiple queries of the following types. Update the value of an element in nums. Calculate the sum of the elements of nums between indices left and right inclusive. Implement the num_array class, which initializes the object with an array integer array nums. Update a particular value at an index to be val. Return the sum of the elements between this and that. Okay. And how many numbers would there be? 3 times 10 to the power 4 numbers. You could use definitely use like a range tree, yeah. But do I need to? Because I really don't want to implement that. Suffix sums. So whenever you update, you have to update the suffix sums. That's like no better than doing this. So it's not suffix sums. It would be range tree. Fuck, how do you do a range tree? Okay. Right, so you can really just have a binary tree. And you could use like pointers for that, but the most efficient way is to actually represent it as a single array. How large would this array be? The number of elements that you need would be 2 times the size of the number of leaves. Do I need to take this to take the closest power of 2? I think I should. Alright. Let's take the closest power of 2. I think that would work. So what is the closest power of 2? 30,000. What's 2 to the power of, I don't know, say 16. 65,000. What about 15? 32, okay. It's 2,768. So 2 to the power 15 would work. 2 to the power 15. So it would be 2 bit shift 15. That's the size of the array that I want. Let's call this the tree, and a bunch of ints inside there. Cool. Now I can implement this update function and then use the update function within the constructor. Okay, let's think for a second how we actually represent a tree as a single 1D array. So it's 0 indexed, right? So 0, 1, 2, 3, 4. 0 would be the root node. But how do we get the left child of the root node? Let's say the root node is index I. Then we would do times 2 plus 1. So that will get the left one. And then the right would be I times 2 plus 2. And the root would be I. Right, so that's the formula that we would use to find out child nodes. Okay, so how do we know we're at a leaf node? Alright, so let's say we have this binary tree, and these are the indexes of the leaf nodes. Let's say, for example, that we want to update this leaf node with index 2. What we do is we start with a range from 0 to 8. So this isn't like the total number of nodes, this is just working with the size of the leaf nodes. If we go from the root node to the left node, or to the right node, we want this to mean that we are halving this range. So if we are going to the left node, we want to half this so that we get 4, something like that. Otherwise, if we go to the right, we get 4 to 8. How do we know whether we want to go to left or right? We get the mid, right? So the mid is 4, these two values, 4, and we check is 2 less than 4? Yes, that's true. So we want to go to the left because this is the middle, right? Even if we were want to change the value 3, we check if 3 is less than the middle, which in this case is 4, and it is. So we go to the left. And that would make sense because the node corresponding to 3 is on the left branch of the root node. So what do we do now? We went to the left side, and now we need to decide whether we want to go to the left child of this node, so this one or this one. Well, what we do is we repeat the same thing. So we take half of this, so the mid of this would be equal to 2, and we ask, is 2 less than 2? Well, 2 is not less than 2. That means we actually want to take the right branch. So we go to 2, 4. So we go down here, and then we repeat the same thing. So what's the middle? The mid is going to be, well, 4 plus 2 divided by 2 is 3. Now, is 2 less than 3? Yes, it is. So we take the lower half of this range, it would be 2, 3. This range only has one element in it. So we've gone down here because we're at the leaf node. This range only has one element, and that makes sense. That means we have found the node within the entire 1D array representing this binary matrix, and we can update it. What should the value of these nodes be? Because right now they're empty. We already know the index of them because that's just the way it's ordered. But we can actually store something here, and that's the key to segment trees. When we go back up, we want to update the value of each of the nodes that are along the path down to this node that we updated with the difference. So let's say we have the value here, and we updated this original value 3 to 2. So that's a difference of -1. So we propagate the -1 up the tree and just subtract -1 from each of these values, and that would work. So that's how we update a value. What about when we query the sum of a range? Well, a range could be any range, right? It doesn't have to be restricted to a particular branch, right? It could go across branches, something like this. In this case, you have to get the sum of the value at this node plus the value at this node, this one and this one, and that would be the sum over this range. So say, for example, we expand this range to here. That means we sum up this node and this node. What if we expand this further? That means we sum up this node and this node. If we have a range spanning over the whole thing, then we just return the root, this node here. Okay, so let's try an example. Let's do this range here. So what is this range? This range is 3 to 6, not inclusive of 6. Okay, and we start off with the range as before, start off with the range of 0 to 8. So currently we're looking at the whole thing. Okay, we want to kind of minimize this to 3, 6, or split it up. So how do we do that? Well, we look at the min range, at the left end of this range. We ask, is this value less than or equal to this value here? So what we can do is actually, you have a 0, 8 here, so we find the middle, which is 4, and then we ask if is 3 less than 4? If it is less than 4, then we can create a splitted range from 3 to 4, not inclusive of 4, something like that. And then we ask, is the right end of this range, so if this is L and R, if R is greater than 4, then we create another range, 4 to 6. Then we pass these ranges down to the next nodes recursively and do the same thing, except that we compare this range to the new range 0 to 4, and we compare this range to the range 4 to 8, right? And this would be another pair. And we keep repeating. And when do we stop? Well, let's just finish this example. So the middle value here would be 2, and so the new ranges here would be, although it would only be one range for this, because we see that 3 is not less than 2. Since 3 is not less than 2, we can't create a left range, we just have a single right range. Then we also ask, is 4 greater than the mid here? Oh, well, it is greater, so we can create a range from 2 to 4. We can compare this with the range 2 to 4. Since they match, we can stop because we found the node that contains the answer for us, and that's this one here. And we do the same for the right down here, and it should be the same. We can try it and do that. Once we found out the answer, so that's pretty much it. We can try implement that. The thing to note is that the size of the array representing this entire binary tree is at least 2 times as large as the number of elements, as in the number of leaf nodes. Notice how that we always divide this range by 2, so the right range is here by 2. We expect that to be a clean division, so it would be good if we use a power of 2 for the number of leaf nodes and the number of elements used to represent the entire binary tree. So let's make it const static int max n equal to 2 bit shifted 15 times. And what we need to do here is create a function called update. This would take in the index I, int value to update with, int the start of the range and the end of the range. If the end minus the start is equal to 1, that means we're at a leaf node. So we can update the value at start, because that would be the node the leaf node corresponding to int I to be equal to value. But before I do that, I want to record the difference, because that's actually what I want to return. And that would be value minus tree start. Then we can return the difference. If we haven't reached the leaf node, we need to calculate the middle value, which is equal to start plus the end divided by 2. If I is less than mid, like we talked about, actually, instead of returning the difference, we can do it another way, and I'll show you later. But let's call update here, pass in I, which stays the same, and value. So if I is less than mid, we want to use start as the start value and mid as the end value. Else, we want to mid to end. Now we need to update the tree. We need to know what node we're currently up to in the tree. This is the index within the leaf nodes, but we actually need the index of the node itself, which I can say is node index ni, and that can start at 0. So that means I need to pass in ni times 2 plus 1. That makes sense because, and it actually might make more sense if we use ni here as well. And this should be plus 2. Cool. And this value should be here. So we want to update ni to be equal to at its left child, which would be ni times 2 plus 1. And the right child as well, which is plus 2. Okay, so that's updating, and hopefully that would work. Here I just have to call update for this index, for this leaf node index. The index within the array representation of the tree. We start at the root node, so it's 0. The value here, the start would be 0, and the end would be max n. For the sum range, let's create another function called sum range. So remember that we have two ranges. So we have L and R, and we also have the start and end. We also need to keep track of what index we're up to, of what node we're up to. So let's do that as I. Now the base case is if these two ranges match, then that means we can just return the value at I. So if L is equal to start and R is equal to end, then return the tree at I. Otherwise, we need to create those ranges. So the middle value will be equal to the start plus the end divided by 2. If the left end of the range is less than the mid, then we want to call sum range on L to mid, and this will be start to the mid. There's still a problem though. What happens if R is also less than mid? Then that means I actually want to have an R here. So I want to do min of R and mid. Similarly, if R is greater than mid, so I'm going to do sum range starting from either the max of the left and the mid, or R itself. And this would be from the mid to the end. And we have to keep track of an answer starting at 0, so we can add to this answer whatever these sum ranges return, and just return that answer. I need to make sure I actually also add, should keep track of which node we're up to. So it would be I times 2 plus 1 here, and this would be I times 2 plus 2. That's important for this part here. And for this part, I just need to return sum range. Now their right is inclusive, so I want to do right plus 1. My start and end would be 0 to max n, and the root node would be 0 initially. Now I just need to initialize it, so I can go through. So I can go through each number and do an update on I, starting at 0, the current value, which is nums I, start and end will be 0 to max n. Should be index here. By the way, this shouldn't be 2, this should be 1. And also, I'm returning something here, but I shouldn't, because it's a void. The other thing is, I realized, I thought this would initialize everything to 0, but apparently it doesn't. What I could do is make this a vector instead of ints, called tree with this many elements. But I can't initialize it here. I have to say tree is equal to a vector of ints of size 1 which shifted 16 times to the left. Okay. Alright, seems to be working. Let's submit this and see what happens. Maybe it'll work. Awesome. That works. Thanks for watching. Like and subscribe, and I'll see you in the next video. And what's the time complexity for this? The update function is just going one path down the tree, which takes log n time. The range query would take log n time as well. It's log n to do a single update or a query, but we have n of those calls, so it's n log n.